Okay, so I just hit record, so we're live. Let's go back to our sheet. Okay, so vertical motion does experience an acceleration. Okay, that acceleration is due to gravity. Gravity is the force with which the Earth pulls on objects, and that force causes objects to accelerate when they are in free fall. Okay, so in topic 2, you probably read that the acceleration due to gravity is represented by the variable g, okay? And that g has a constant value. It's equal to negative 9.8 meters per second squared. Okay, so that's a constant that you're going to want to have memorized, okay? Negative 9.8 meters per second squared. That's always, always, always the acceleration that an object experiences when it's in free fall, okay? So, key thing to remember, horizontal motion, no acceleration. Vertical motion, acceleration is equal to g, all right? Okay, so we're gonna go through these steps in the context of an example. I've kind of set up kind of the framework that I use to solve these kinds of problems. So what I always do, I always have my equations available to me just so I can identify the equation that I need to solve a particular problem. And you know, when I get that equation sheet out there, that'll make your job easier as well. I also put a blank set of axes right here so I can kind of draw the problem. And then I've put some workspace down here for our horizontal equation that we're going to use and our vertical equation. Remember, it's so important to get your components resolved so that you can work with them separately. Okay, so let's read this problem. It says, a projectile is launched at ground level with an initial speed of 50 meters per second at an angle of 30 degrees above the horizontal. It strikes a target above the ground 3 seconds later. What are the x and y distances from where the projectile was launched to where it lands? Okay, so if you were looking at like a visual representation of this problem, let's say that here's my projectile's path. It's gonna leave the ground. It's gonna peak. Gravity's gonna take over. It's gonna fall. Splat. Okay. On this empty set of axes, however, we're not gonna draw the actual path the object takes. We're just gonna be dealing with the velocity vector. So this is what the situation is gonna look like in real life. Okay. But we're going to deal with the physics over here. So what we're going to do first is draw our velocity vector. Now they told us our velocity vector is 50 meters per second. Okay, so I'm going to draw that coming out of our origin. Okay, so let's say that here's our vector. It's 50 meters per second. So I'm going to label it 50. Okay. They also told us that this object was launched at an angle of 30 degrees above the horizontal. Okay, so let me pencil that in real quick. So 30 degrees. Okay, so we just drew our situation. The next step is to resolve your components to get your x and your y values. Okay, so just like last time, we're going to make this into a right triangle. Okay. So here's our vertical component. Here's our horizontal component. All right. So using SOHCAHTOA, I know that the sine of 30 degrees is going to be equal to the triangle's opposite side over its adjacent side. Not opposite over adjacent, excuse me, opposite over hypotenuse. Don't want to confuse it there with tangent. Sine is equal to opposite over hypotenuse. So the opposite side of 30 degrees, I don't know what it is. We'll call that our y component. I do know my hypotenuse, however. That hypotenuse, the problem told me, was 50 meters per second. Okay? So if I solve this equation for y and just multiply that 50 over to the other side of the equal sign, okay, hopefully you have your calculators handy so you can do this with me. The sine of 30 degrees, if I times that by 50, I get a y component of 25 meters per second. meters per second. Okay, give me a thumbs up if you feel good at this point. Okay, good. Don't hesitate to stop me if you have questions. For the x component, we're going to do our cosine. So the cosine of 30 degrees is equal to the triangle's adjacent side, which is x, over the hypotenuse. Okay, so x over 50, same drill. Multiply that 50 over to the other side to get your x component. So in my calculator, cosine of 30 degrees, if I times that by the 50, I get x by itself, and I get an x component of about 43.3. 43.3 meters per second. Okay, always, always, always do that first. Resolve your components, and then we're going to do the math now. So once I've got my components, I've got my workspace for my horizontal equation right here, my vertical equation right here. So this 25 meters per second, that's a y distance. So that's going to be going down here in my vertical workspace. I'm going to be dealing with my 43.3 meters per second over here in my horizontal workspace, since that's in the x direction. Okay, so I highly recommend kind of setting up your homework workspace like this. It's going to keep you very organized. Okay. So now comes the trickiest part, and this kind of relates to the question that was asked about 10 minutes ago. How do we know which equation to use? Okay. So let's go through the list of equations in this box, and I know they're kind of small. I kind of had to shrink them down to make it so that this all fit into one space. But take a look at what the question's asking you. They're asking you, what are the x and y distances from where the projectile was launched to where it lands? So that's your key word. They're looking for distance here. Okay, so I can cross off my equations that are solved for v, because those are equations that will get me velocity. I don't care about velocity. I want distance in this problem. I can cross off this last one. It's also a velocity equation. That leaves me with two equations left that deal with distance. Remember, x is your variable for distance. Okay, so I've already crossed off three equations that aren't really going to help me in this scenario. I've got two remaining. Okay, if you look at the top one, we have x is equal to x naught plus v bar times t. Okay, but remember, v bar, this variable right here, we talked in our videos last week that v bar is our variable for average acceleration, or not average acceleration, average velocity, excuse me. So this is average velocity, but they didn't give me average velocity, they gave me an initial velocity. So I don't really need this one either, okay? Which leaves only this fourth equation that could work. So let's just double check to make sure all of the variables are accounted for. X is gonna get me what I want. That's gonna give me my distance that I'm interested in. X naught, that's our initial position, okay? So our initial position, since we're starting at the origin of this XY plane, that's gonna be 0, okay? V naught, okay? V naught, if you remember from the video, V naught is a fancy variable for initial speed, okay? So let me kind of write some stuff up here just so we don't get too messy. So initial speed, whenever you see those words, that's your V naught, okay? Going on with the equation, we have V naught times t. Well, in the problem, they gave us t. They said this problem was 3 seconds, so that's my t value, okay? And then continuing on, it's plus 1/2 times at squared. Well, what's my a value? Okay, well, since this is a projectile story problem, what acceleration are we experiencing, guys? I just talked about this 15 minutes ago. What's our a value? What's the only acceleration that this object is experiencing? Gravity, yeah, gravity. So my a value, even though the problem didn't state it, because this object is being subject to gravity, my a value is actually going to be my g value, which is -9.8 meters per second squared. Okay, so remember that anytime you have a projectile, your acceleration is going to be negative 9.8. Okay, so hopefully I've demonstrated to you that that fourth equation is our best bet for getting our answer. Okay. So for those of you who are listening in, are you okay up to this point? Give me a thumbs up if you're good. Give me some questions, guys. What questions do you have? Any questions?
How exactly did you find 43.3 meters per second again?
Okay, good. So the way I did that, remember over here, our x component is, we're going to get that by setting up our right triangle. Cosine of 30 degrees. Remember, cosine in SOHCAHTOA, cosine stands for adjacent over hypotenuse. So in our triangle we drew here, if you look at your angle, right adjacent to that angle is our unknown x. Okay? So since cosine is equal to adjacent over hypotenuse, my adjacent is x. I don't know what that is. My hypotenuse, they gave me as 50 right here. Okay, so adjacent over hypotenuse. Now, how am I going to get x by itself, guys? Shout it out. Multiply. Yeah, to get x by itself, you got to get this 50 away from x. Okay, so using inverse operations, since x is being divided by 50, to get 50 out of the way, I need to times both sides by 50. Okay, so if I times both sides by 50, times by 50, times by 50, these 50s will cancel. And then my answer for x should just be whatever 50 times the cosine of 30 is. Okay, now when you plug that into your calculator, you should get about 43.3.
Thank you.
Does that answer your question?
Yeah.
Okay, good. All right, so we've decided on an equation. We need to do it twice. We need to do it for the horizontal aspect of this problem. We also need to do it for the vertical aspect of the problem. So let's do horizontal first because it's easier. So in my equation, x is equal to x naught. Well, since my problem is starting at the origin of this coordinate plane, my x naught is going to be 0. Easy. We're going to add to that v naught. Okay, my v naught, remember, was the initial speed that they gave me, but in the x direction. So my v naught in the horizontal direction is this 43.3. Okay, so I'm going to plug that in for v naught, 43.3. I'm going to times that by t, just like our equation tells us to, my t being 3 seconds according to the problem. And I'm going to add that to 1/2 at squared. So 1/2, my acceleration we just said a couple minutes ago was negative 9.8, just like it always is. Oh, sorry, I almost made a mistake. Remember in the bullet points up above, horizontal motion never experiences acceleration. Okay, write that down in your notes if you haven't already. Horizontal motion never experiences acceleration. So my a value in my horizontal direction is 0. And then my time is 3. And just like the equation says, we're going to square that. Okay, so from now, we just got to plug and chug. Plug this into your calculator and figure out what you get. So the great thing about horizontal motion is that we have a whole bunch of zeros here. Okay, so this whole term where we're timesing by 1/2 at squared, since acceleration in the horizontal direction is 0, this is just going to go away. We don't care about it. It's going to cancel out. So we're just left with x being equal to 0 plus the product of 43.3 and 3. Okay, so when we do that, 43.3 times 3 gives me 129.9. 129.9. And since this is a distance, the units are meters. Remember, x measures distance. So what this tells me is that in the original problem, we're launching this projectile whether it be a cannonball or something, we know that it traveled a total horizontal distance of 129.9 meters before it hit the target. Okay, now comes the vertical side of things. So we're going to do the same equation that we chose up above, but we're going to plug in our g value for our acceleration. Okay, so just like we did for horizontal, x is equal to x naught. Once again, we're at the origin, so x naught 0. We're going to add our v naught, which in the vertical case was this number up here. My vertical component was 25 meters per second. So 25 times our time, which hasn't changed. That's still 3 seconds. Okay, and then I'm going to add on to that 1/2 times g, since that's our acceleration, so negative 9.8, times my time squared. So times 3 seconds squared. Okay, so this takes a little bit more work in your calculator, but it's pretty manageable if you know what you're doing on a calculator. So 25 times 3 seconds gives me 75. So that's what this middle portion is. If I type in 1/2 times negative 9.8 times 3 squared, I get, for this other term, I get negative 44.1. Okay, if I subtract those two values from each other, 75 minus 44.1 gives me 30.9. Okay, so 30.9 meters. And that's my vertical distance that this object travels. Okay, so we've solved the problem. Let's just make sure that it makes sense, and then we're done. Okay. So remember, in this upper left-hand corner, I kind of showed you what this would look like in real life. Launching a projectile, you launch it, it reaches a maximum height, it comes back down. Okay. Well, let's just kind of examine this again in terms of our problem. So I'm going to draw a blank set of axes, and we're going to storyboard out what actually happened in this problem. So our projectile was launched, okay, at an angle of 30 degrees. Gravity took over, it reached a max height. But according to our final answer, it hit a target that was a horizontal distance of 129.9 meters away. And that target was 30.9 meters in the air. Okay, so probably something like this. So let's say that here's our target, and we can draw like a little bullseye in there if we wanted. There's our target. Okay, so it traveled a horizontal distance of 129.9, and it traveled a vertical distance, so it ended up vertically only 30.9 meters off the ground. 30.9 meters off the ground. Okay. How are we doing? Give me a thumbs up if you're with me. Give me a thumbs up if you feel like you could do this on your own without any help. Okay, yeah, it's intimidating, I know. For those of you who are saying you're confident that you could do this on your own, I'm proud of you. But you'll need to practice this a lot. You know, even those who are confident, you're probably going to make a mistake your first time you try this on your own. Okay, so go back, reference this video as many times as you need to kind of see how we set up the problem. Set it up with the same kind of framework that I showed you here, where you have different workspaces for different aspects of the problem. And that way you're going to keep yourself organized. I just got to say, and this is kind of where I get a little bit nerdy here. It's so cool that we can do math and figure all this stuff out, okay? You can figure this out for anything you launch into the air, a cannonball or an arrow that you shoot with a bow and arrow. these equations will give you a good estimate for where these objects will land. It's just really cool that we know all this. Okay, now there is one caveat though. These equations neglect the effects of air resistance. Okay, so we're ignoring the impact that air resistance has in these cases. Okay, now for objects that are pretty massive, air resistance isn't going to have much of an impact anyway. If you launched a bowling ball into the air, these equations would probably do a pretty good job of estimating where it's going to land. If you launched a paper airplane into the air, though, which is pretty susceptible to air resistance, these equations won't be as accurate. Does that make sense? Give me a nodding if that makes sense. Okay, good. Really, guys, that's the main thing I wanted to do today, is just to kind of show you one of these projectile problems, just so you could be more comfortable with how they're set up. So let's open it up for any last minute questions. What do you guys have for me? Okay, it's quiet. Mr. Schmitz, is there any questions in the room?
It looks like we got one.
One question.
Is there any way we can like extend the date for topic 2 till Sunday?
I can do that. Yeah, let's do that.
Awesome. Thank you.
Okay, so Sunday by midnight. Are we agreed?
Yes, sir.
All right. Thanks, guys, for logging on for a short time this morning. Have a good rest of your day. Keep those emails coming to me so we can keep in touch. And good luck, okay?
Thank you.
We'll see you later.